much. My name is Sofia Celi, and I'm a senior researcher at Brave and also University of Bristol. And as I said, I'm going to be talking about how to thresholdize MLDSA. And the name of our skill is Mithril. And if you're interested in learning more about it, I invite you to look at our Usenix paper or also the website. And this is a joint work with Rafael Del Pino, Thomas Espito, Guillaume Niot, and Thomas Prest. Okay, so today, as in the previous talk, we're essentially going to be talking about threshold signature, which is essentially a distributed version of a signature. And what we aim to do is essentially that T out of n parties can collaborate to sign a message, and T minus 1 parties cannot sign. And essentially what we want with this type of schemes is to arrive mostly to these two properties that you see on the slide. So we want first correctness, which means with at least T out of n partial signing keys, we can indeed sign. And we also want unforgeability, which means that whatever scheme we are designing should remain unforgeable even up to T star parties that are corrupted, where T star is less than T minus 1. Okay, so that is essentially what we want. So you actually want to have a threshold signature. What you essentially are going to be having is all of these sub-processes that you see on the slide. First, you're going to have a mechanism in which you take a secret key, and you're going to be generating secret shares of that specific secret key in association with the verification or public key. Then you're also going to have a procedure in which what you generate are partial signatures that later you're going to combine into a full signature, and that is going to be the output of your threshold signing procedure. And then the verification procedure just works as any of the single party verification procedure that just verifies the signature in relationship to the public key. Okay, so if we want to thresholdize something, what we do is that we start by looking at the signature scheme and seeing which specific routines of that specific signature scheme can be made distributed in some generic way or other form. And then what we also want is to have some kind of key distribution procedure and a way to actually create shares of that specific secret key. And what we end up, if we have those two, is specifically to a threshold signature procedure. Okay, so now let's start looking at MLDSA. MLDSA is currently an algorithm that has been standardized by NIST after all of the post-quantum process, and essentially this algorithm is based in lattice-based cryptography. So I'm not going to go into details of what lattices are, but essentially in cryptography, we're mostly interested in the two problems that you see here, the short integer solutions ones and also the learning with errors. And essentially these allow us to create cryptographic schemes that are secure under these specific assumptions. Again, I'm not going to explain you what these assumptions are, but later we will see in our threshold signing procedure when we actually reduce to these specific assumptions. Okay, now let's start with the first part that we talked about when trying to create a threshold signature. Is first let's look at the signature to see how we can actually thresholdize it. So how would you actually create a signature under the lattice assumptions following what MLDSA does? So essentially what you do is that you start with a simple identification protocol, or what we usually also call in the literature as a sigma-based protocol. Why a sigma-based? Because essentially you have 3 rounds, right? You have a commit, a challenge, and then an answer. And you also have 2 extra procedures. You have a key generation and a verification. And this specific algorithm runs between a prover and a verifier. So in the first procedure that we have, the key generation, you essentially have a way to generate a secret key and also an associated verification key. The secret key under the lattice assumption should be short, and the verification key is just something that you generate by generating a random matrix A and multiplying via the secret key. And the result of that is going to be the verification key. Now we go to the actual kind of like signing procedure, though in this case, all that we're doing is proving knowledge. So the first step of this procedure, the first sub-step of this procedure is further commit. For committing, what we essentially do is that we sample a short R, and then we multiply that with the matrix. And the result of that is going to be this W, which is the commitment. We send that over the network, and then the verifier takes that, and in turn generates a challenge, which is also short, and send that specific challenge over the network. Once the prover receives that specific challenge, what they do is that they compute an answer that we call Z, which is just the result of the multiplication of the challenge times the secret key plus the randomness. And this is great, and this works. But there's a problem with this that you already will know when you're actually trying to create a signature, which is essentially that this specific procedure is an interactive procedure. And we don't want that. We want a non-interactive one. So what we do is that instead we use a transformation or a compilation technique, if you want to call it that way, that is called usually the Fiat-Shamir transform, to essentially transform that specific interactive protocol into a non-interactive one. And the way that we do that is that we fix the challenge to be the same both at the prover and verifier side. How we do that is by taking the challenge to just be the hash of the commitment that you sent in the first round. You can also use any other transformation. The Fiat Shamir is not the only one, but we usually will be using the Fiat Shamir one. Okay, and with that, essentially you have a way to create a signature, and you want to look more like at the algorithmic level, it will look like this. The verification is the same, but now in the signature procedure, we have all of the steps of the Sigma protocol with the Fiat Shamir transform. And the verification is the same. Essentially, it's the same as a single party signature. Essentially, what you do in the verification is that you give the ability to recover the W from the set, and you also verify that that specific set Z is short. Okay, and as I told you, I was going to actually show you how certain parts of this specific algorithm reduce to some hardness assumptions, and here they are, if you're interested. And in MLDSA, as you see here, essentially this is the algorithm. You have the verification, you have the signature one, and then you also, you have the generation, the signature one, and you also have the verification. But there's a trick. So if essentially you were looking at the previous slide and say like, oh, this looks very simple, we can just apply any kind of distributed technique, MPC technique to thresholdize this. It is true, but there's a caveat. The problem is that in MLDSA, you have to also perform a specific operation that we call rejection sampling. What is rejection sampling? It is a technique so that whatever set you send over the network doesn't really reveal any of the distribution of the secret key. Because if you look at that equation, the equation of Z, you see that there's a direct relationship with the secret key. So just sending it like that way would actually reveal over time information of the secret key. And we don't want that. We want that the distribution is independent of that secret key. And for that, we use rejection sampling. Using rejection sampling is also great because it means that we can also reduce the size of the signature. And usually in the literature, you will see that this is called as Fiat Shamir with abots, because with some probability, sometimes you will not find that a specific short signature that is independent of the secret key. And in those cases, you have to restart. So if you're already familiar with doing thresholdizing techniques, you already know that this is the crux of the difficulty, because actually doing this, the rejection sampling in a threshold matter, is what is the most difficult. Okay, so now let's return to actually create a threshold signature. Now we have a signature scheme, and we know that we can thresholdize this. Now let's look at actually how to generate secret shares of a secret key so we can actually distribute them to all of the signers in order to create a signature. And for that, the question will be, if I have a secret key, how can I generate a small shares of that specific secret key? The technique we introduced in our paper is essentially called replicated secret sharing, which is a way of generating short secret so that anybody can take them and eventually with all of them reconstruct the secret key. What does it mean? Essentially, we have this secret, the SK, that now is going to be shared as the sum of m, which is n choose n minus 1 plus t, which essentially means that for any act of t users, the union of all shares fully covers the shares, but for less than t, there are unknown shares. So let's look at this example. In this example, we have n is equal to 4 and t is equal to 3. Applying the question, we will have an m that is equal to 6, and hence we have 6 shares as you see in the slide. How we're going to give that to the specific parties is that we give to the blue party the 2 shares, to the yellow one 2 shares, and also to the purple one 2 shares. And jointly together, they can reconstruct the secret key. And this is great because now we have actually a way to generate a small shares or coefficients, but this is not great for efficiency because it requires exponentially many shares. And that is one limitation of our protocol, is that we only work with a small n. So n is usually equal to 8 or equal to 6, because if not, if we increase, we will have to increase exponentially the amount of shares that we have to distribute to the different parties. Okay, so with that, now we have a signature scheme, and we also have now a version of actually how to create short secret shares of that specific secret key. So now let's look at the threshold signature itself. So back to the threshold. So first things, we're going to be having the key generation, which is essentially that we're going to be having the verification key, a secret key associated to that verification key, and we're going to be generating short secrets of that secret key. Then we enter the actual signature procedure, and what the first thing, if you remember in MLDSA, is that we generate that commitment W. So we're going to be doing the same in threshold signatures. We're going to be generating the commitments of all parties. Then what we're going to do is that jointly we're going to be agreeing together on a specific challenge, C, as in MLDSA. And then we're going to be generating partial signatures that later we're going to combine in order to generate the signature. And the verification procedure is the same as a single-party MLDSA. More at the algorithmic level, it literally looks like this. In the first run, essentially we generate the commitments per party, and we commit to those commitments via the hash function that you see there. In the run 2, we broadcast those specific commitments W, and in run 3, essentially we do just the generation of the answer set. And in the combine, we also just like took all of the material that is sent and we combined them together to generate the signature. As you see here, I told you that we have to do rejection sampling, right? Because if not, we are going to be revealing the distribution of the secret key. Sorry, we're going to be revealing the secret key over time, so we don't want that. So we have to perform rejection sampling. In our algorithm, we decided to perform rejection sampling in 2 places. Both at the partial signature, so we check that each individual set is correct, and also when we actually combine. The reason why we do this is that for the first case because of security, and for the second case because we wanted to be compatible with MLDSA. Okay, and again, why we want rejection sampling is essentially because usually the signatures will be too big to pass verification and also will be insecure. So what you do is that you add rejection, and you reject until the distribution of the signature is small enough. Okay. Now, prior to showing our trick of how we actually do rejection sampling, so we have something efficient in a threshold manner, let's talk about a little bit more practicality and what we wanted to have in our scheme. The first thing is that we wanted to have some properties. We wanted our scheme to be practical, which essentially means that we're going to be generating signatures with high probability. Remember that I told you that the algorithm is probabilistic. So with some probability, sometimes you will not find a short signature that will work for you. But we don't want this probability to be very high, right? It will be impossible for a user to be waiting forever until a signature is correct. So we want actually that probability to be low. So we want to be practical. We also want compatibility, meaning that whatever signatures can also be usable by the verification algorithm of single-party MLDSA. And we also want to be secure, which is security under real-world assumptions, as for example, dishonest majority, active security, and adaptive security. I'm not going to be touching the security part because this is the subject of future work, but it's a really interesting topic, so I invite you to actually think about it more deeply eventually later. Okay, so for the first 2 properties, which was practicability and also compatibility, let's look again at rejection sampling. And for this, let's look a little bit at MLDSA's rejection sampling. MLDSA essentially uses what is called the infinity norm, which essentially means that the rejection region is a hypercube. But this is not great, because if you actually just do this in a threshold manner, it will be really inefficient and the probability of aborts will be too high. So we don't want to directly use the hypercube. What we do in our paper is that we exploit the slack of MLDSA norm bounds. So instead of using the hypercube that is usually used in MLDSA, we use another geometric figure. Why we want this? Because if you look at the geometrical part of this, you will see that there's an unused geometric slack. So this will be a little bit inefficient to actually use directly in a threshold perspective. So what we did is that we changed the figure. We changed the geometric representation. Instead of using directly the hypercube, what we decided to use is a hyperbola. Because as you see in the slide, everything becomes tighter. So it is much more efficient, and we will have less abort probabilities by using this specific figure. So it is just a trick of geometry in order to make everything more efficient. The problem with this is this again will exponentially degrade if we use many parties. So again, with this specific technique, we're again locked to only be able to use, for example, 6 or 8 parties. Okay, so now we have a practical scheme because we can create signatures with high probability, and we also have a compact signature size. But as a caveat, we have a limited amount of parties. And also another caveat is that our signatures are not indistinguishable. While they do pass the single-party verification procedure of MLDSA, they are distinguishable. Why? Because if you remember, in MLDSA, we're sampling from the hypercube. But in our signature, we're sampling from the hyperbole. So that means that we have 2 geometrical differences, and hence whatever is the result of our signing procedure is going to be distinguishable when compared with single-party MLDSA. Okay, and we still have security because we have a fungibility under the same MLDSA assumptions. 2 more properties that we also wanted to have. Efficiency. Our scheme actually arrives to 2 offline rounds and 4 online rounds, which is currently the state of the art. And we're also practical because the first run can be performed independent of the message. If you remember when we sampled that specific W, we don't depend at all on the message, which is great because it allows for preprocess and also allows for safe concurrency. Let's look at numbers. So both from a communicational and also computational perspective, we have a highly performant scheme. Again, with the caveat that we can handle at most 6 parties. So for many choices of 2 and 6, for many choices of N and D that are vary between 2 and 6, we have that the scheme arrives to kilobytes. And also from the computational perspective, we have a scheme that is very performance because the majority of times for both key generation, sign and combine, we arrive to the milliseconds. We did an implementation in Golang, which is not the most performant language, so maybe these times will actually improve. And we also didn't include any kind of software or hardware optimization, so maybe again these times can be improved. If we compare with the state of with related work, currently we have the best scheme in terms of communication, computation, and also the number of rounds. But again, always with the caveat that we have a limited amount of parties that we can use. Eventually, when we cross the threshold of the number of parties, our scheme will essentially start to degrade. If you're interested more from a practical perspective, we did decide to launch our scheme as part of a one experiment. So what we did is that we integrated our threshold signing procedure into a library that is called libpeer2p to actually check how our scheme will behave under interesting network conditions. And what we actually found out is that our result shows that the overall impact is the critical path. So what actually impacts in the numbers is the latency of the network and not much the computational times introduced by the threshold signing procedure. So for example, we launched a specific experiment between Taipei, Seoul, and London, and we arrived to a signature in 750 milliseconds. Okay, and maybe your last question will be, how can we use this scheme? If you have an actual application that is comfortable with using, for example, 6 amount of parties, this is a really nice to use scheme. And currently in the literature, there's some suggestions that sometimes when you're trying to integrate threshold signatures into wallets, it is enough to, for example, having 6 trusted wallets in order to use this specific scheme. The same can be said for example, when you're trying to introduce threshold signatures in the post-quantum PKI and TLS infrastructure, or you're trying to integrate it in critical infrastructure as, for example, the Tor network. In the Tor network, for example, it depends on the number of directory authorities that jointly generate a randomness and need to sign that specific randomness, but they often vary between 10 or 8 directory authorities, so maybe our scheme can still be suited for those specific cases. For future work, we're thinking of many things. So we're actually thinking of expanding the security, as I told you, for both active and adaptive security. And we're also thinking of actually doing optimizations, both at the hardware level to arrive to something that is even more performant. And as Giacomo said in the previous talk, we're also actively doing a submission to the NIST threshold call. So we'll eventually will be working for a full implementation, a full specification. Okay, and with that, thank you very much. And if there's any question.
Okay, thank you, Sophie. Do we have questions for Sophie? Okay, maybe I can start with a quick one. Sophie, do you know some concrete use cases that really need the signature to be indistinguishable? Because I cannot think of any.
Okay, so we actually don't know of specific cases, but we don't also know if there will be attacks. And that is something I'm currently thinking. So sometimes, for example, if you have been looking at password-based authentication key exchange, sometimes there are attacks because of the indistinguishability, and you can mount what is called partition attacks, which essentially means that you're giving an adversary, for example, information about the signature via the distribution, and later you can recover the password or the key because of that. Maybe in this case, maybe some of those attacks could also apply, but it's currently not explored in the literature. So yeah, I would be worried more than application, I would be worried on potentiality of attacks.
We have time for one more question. Okay, no, in that case, let's thank Sophie again.